Hey guys, Mr. Backerberg here. This is our test number 4 review video. Taking a look at the first section, we are asked to perform the operation and then write the result in standard form. Example number 1 says we're going to take 7 plus 2i plus 1 minus 4i. Since we're adding these complex numbers together, what we're going to do first is we're going to add up the real numbers. So 7 plus 1 is 8, and then we're going to add up the imaginary numbers. 2i plus negative 4i is negative 2i, and that's going to be the answer for this one. In number 2, we're doing some subtraction, so I'm going to distribute that negative through to turn it into an addition problem. Then we have to take negative 7 plus 9, which is 2, and then 5i plus 11i gives us 16i, and that's our answer for that one. Number 3 looks like we have to do some distributive properties. So I'm distributing the negative 3i to everything inside of the parentheses. Negative 3i times negative 5 should give us positive 15i, and negative 3i times 7i should give us negative 21i squared. Remember, I squared is the same as negative 1, so if we take the negative 21 times the negative 1, we get positive 21, so this is 15i plus 21, but then we want to write the result in standard form, so that real number should come first, so 21 plus 15i. If we look at number 4, we're multiplying some binomials together, so we have to FOIL that out. So if we take the 7 times the negative 2, we get negative 14. 7 times negative 3i is negative 21i. Negative 5i times negative 2 gives us positive 10i, and negative 5i times negative 3i gives us plus 15i squared. Again, this I squared is the same as negative 1, so negative 1 times 15 gives us negative 15, and if we combine that with the negative 14 at the beginning, we get negative 29. Negative 21i and plus 10i becomes negative 11i. And then the last one, we're taking 2 plus 3i squared, so that means we've got 2 plus 3i times another copy of 2 plus 3i. So this one is a FOILing problem. 2 times 2 is 4. 2 times 3i is 6i. And 3 times 2 is another 6i. 3i times 3i is 9i squared. I squared is negative 1 again, so this negative 1 turns the 9 into a negative 9. And if we combine that with the 4, we end up with negative 5. And then 6i plus 6i gives us 12i. Taking a look at 6 and 7, we're asked to write the quotient in standard form. This is where we have to use the conjugate of the denominator to help us out. So on the bottom, we've got 2 minus I. Its conjugate would be 2 plus I. So we have to multiply by 2 plus I on top and on bottom. On top, we're going to distribute the 5i. So 5i times 2 is 10i. And 5i times I gives us plus 5i squared. On bottom, we're going to have to FOIL this out, so 2 times 2 is 4, 2 times I is plus 2i, negative I times 2 is negative 2i, and negative I times I gives us negative I squared. On bottom, we can cancel out the 2i and the negative 2i. This I squared on the end is a negative 1, so if we go 4 minus negative 1, that ends up giving us 5 on the bottom of the fraction. On top, we've got this I squared on the end, so we can turn that into a negative 1 as well. This negative 1 is going to turn the 5 into a negative 5. And then we've got this plus 10i. Now, one thing that we can do is we can split our fraction up. We can take negative 5 and divide it by the 5. And we can take our 10i and divide it by the 5. Negative 5 divided by 5 is negative 1, plus 10i divided by 5 just gives us 2i. Similarly, in number 7, we're going to multiply top and bottom by the conjugate of the denominator. So we're going to be multiplying top and bottom by 2 minus I. On top, we're going to have to FOIL. So 2 times 2 is 4. 2 times negative I is negative 2i. 3i times 2 is plus 6i. And 3i times negative I gives us negative 3i squared. On bottom, again, we're going to have to FOIL this out. And it's going to be very similar to the last one we did. 2 times 2 is 4. 2 times negative I is negative 2i, I times 2 is plus 2i, and I times negative I is negative I squared. Top and bottom, we've got a negative I that we can turn into a negative 1. On bottom, the negative 2i and the positive 2i cancel out. 4 minus negative 1 gives us 5 on bottom. On top, this negative 1 turns the negative 3 into a positive 3, and 4 plus 3 should give us 7. If we combine those i's in the middle, negative 2i and plus 6i should give us plus 4i. And then again, we can split our fractions. We can take the 7 and divide it by 5, and the 4i and divide it by 5. Neither of these reduce, so that's just our answer, 7/5 plus 4i over 5. If we take a look at number 8, we're asked to find the solutions of the equations. This one's a quadratic, so we can look at it and maybe try to factor, but I don't think factoring is going to work, so maybe we decide to do the quadratic formula. So I'm going to go with negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now I'm going to work underneath the radical first and simplify that down. If we take negative 2 and square it, we get 4 minus 4 times 1 is 4, and 4 times 17 is 68. So we got 2 plus or minus that square root all over 2. Now 4 minus 68 is negative 64, so 2 plus or minus the square root of negative 64 all over 2. And the square root of negative 64, well, the square root of 64 is 8, but since it's negative, we get 8i. So it's 2 plus or minus 8i over 2. And again, I would think about splitting our fraction. So I'm going to take the 2 and divide it by 2. And then plus or minus the 8i over 2. 2 divided by 2 is just 1, and 8i divided by 2 is 4i. So we get 1 plus or minus 4i. Now if we look at number 9 and we want to solve this one, I would just use inverse operations. So the first thing I'm going to do is subtract the 8 over to the right-hand side. So we get 2x squared equals negative 8. Divide both sides by 2, and we get x squared equals negative 4. Now square rooting each side, we get x equals, since we did the square root, it's plus or minus. The square root of 4 is 2, but since it's negative 4, we get 2i as our answer. In number 10, we're looking at finding the zeros of the function. So in order to find the zeros, we're going to set it equal to 0. So we get 0 equals x times x minus 6 squared. Now think about what it means to square something. Squaring something means we're going to multiply it by itself. So really we've got 0 equals x times x minus 6 times another x minus 6. Now, most of the time we've been given a polynomial function and we've tried to factor it out in order to find the zeros, but this one is already factored out as much as it can be. So now what we're going to do is we're going to take each one of those factors and set it equal to 0 and then solve them individually. So we get x equals 0, x minus 6 equals 0, and another x minus 6 equals 0. Now this first one's already done, so we get 0 as an answer. If we solve either one of these x minus 6's, we'd have to add the 6 over to the other side. So then we end up with x equals 6. And if we solve the other one, again, we're going to get x equals 6. So 6 is a repeated 0. So for number 10, we just get x equals 0 and x equals 6. If we look at number 11, again, I would set it equal to 0. So 0 equals 2x cubed plus 8x. This one we can do some GCF factoring on. We can pull a 2x out of each one of those terms. Then left over inside of the parentheses, we've got x squared plus 4. Now that we've factored, what we want to do is take each factor and set it equal to 0. So 2x equals 0 and x squared plus 4 equals 0. To solve the first one, I would just divide both sides by 2, and then we end up with x equals 0. For the second one, I'm going to subtract the 4 over to the right-hand side, so we get x squared equals negative 4. Then if we square root each side, we end up with x equals plus or minus 2i as our answers. For 12 and 13, we're looking at using the rational zero test to make a list of possible zeros for the function. Rational zero test is where we do p over q. P are the factors of the constant term on the end, and Q, those are the factors of the leading coefficient at the front. So on top for the p-values, we're looking at things that multiply together to give us 25. So we'd look at like 1 and 25 and 5 and 5. I'm not going to write 5 down twice, I'm just going to write it down once. But what we have to remember to do with each one of these numbers is put the plus or minus in front of it. Now on bottom we're looking at the 2. There's only one pair of factors there. It's going to be 1 and 2, again with the plus or minus in front of them. So this is our list of possible zeros. Now if we look at number 13, again we're looking at the constant term on the end to get the p-values. So things that multiply to 12 are 1 and 12, 2 and 6, and 3 and 4. And again, with all of these, we have to put the plus or minus in front of them. On bottom for our q value, our leading coefficient is just 1, so it's plus or minus 1. For 14 and 15, again, we're going to use that rational zero test, but now, after we get the list of possible zeros, we want to do synthetic division to show which ones actually work. So looking at the 6 to find our p-values, we'd get plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. On bottom, we just get plus or minus 1. Now we're going to guess and check. We're just going to try out some of these zeros to see if they actually work by using our synthetic division. So setting up the synthetic division, on the inside we'd have 1, -6, 11, and -6. On the outside, we're just going to guess and check one of these. I'm going to start with 1. So let's see if that works. We'll drop the 1 down. 1 times 1 is 1. Here we get -5. Multiply those, and we get -5. Add these together, and we get 6. 6 times 1 is 6. And if we add those together, we get 0. Since we got 0 as an answer, that means 1 works as a 0. Now instead of starting all the way over, we're just going to continue off of this one. And again, we're going to randomly pick a number off of our list and see if it works. I'm going to pick 2, drop the 1 down. 1 times 2 is 2. Add these together, we get -3. 2 times -3 is -6. And we get another 0 as the remainder. So that means 2 also works. We've got one more that we can find. Again, I'm just going to continue off of this. And I'm going to try out 3. If we drop the 1 down, we get 1. 1 times 3 is 3. We end up with a 0 remainder, so that means that 3 also works. This is a cubic function, so we should be looking for 3 zeros of this function, and we get x equals 1, x equals 2, and x equals 3 as the zeros for this function. For number 15, again, we're going to set up our list of possible zeros. So we're looking at the 9 for the top, so we get plus or minus 1, plus or minus 3, and plus or minus 9. Now on bottom, the leading coefficient is a 3, so we get plus or minus 1 and plus or minus 3. If we set up our synthetic division, we've got 3, -19, 33, and -9. Setting up the synthetic division, I'm going to try out 3 and see what happens. So we drop the 3 down. 3 times 3 is 9. Add these up, we get -10. 3 times -10 is -30. Add these up, we get 3. 3 times 3 is 9. And add these up, and we get 0. So this is telling me that 3 works as a 0. Now, instead of doing a bunch of synthetic division like we did on the last one, what we could do is now take the leftover things and rewrite it as a polynomial. If we were to do that, we'd get 3x squared minus 10x plus 3. And now this is a quadratic, so we've got a couple of options. We can try to factor it, or we can do the quadratic formula. I do think factoring will work on this one. It's going to be guess and check factoring since we have an a value at the beginning. To get 3x squared, we're going to need 3x and a regular x. We need to multiply to 3, but add up to -10. So I'm going to guess that it's -1 and -3. If we double check it, 3x times -3 gives us -9, and -1 times x gives us -1x. If we add those together, we do get our -10x in the middle. After we have it factored, we're going to set each factor equal to 0. So 3x minus 1 equals 0, and x minus 3 equals 0. For this first one, we'd add the 1 over and divide by the 3, so we get x equals 1/3. For the second one, we'd just get x equals 3. So again, we've got 3 zeros since this is a cubic. We had x equals 3, and that actually showed up a couple of times. And we also had x equals 1/3. That only showed up once. So it looks like there's only 2 zeros, but 3 is a repeated 0. It's showing up multiple times. For number 16, we're going to look at finding all the zeros of this function and then rewrite the polynomial as a product of linear factors. First thing I would do is maybe use the rational zero test to find a list of possible zeros. So we'd go plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12 on the top. On the bottom, we've just got plus or minus 1. If we set up our synthetic division, that's 1, 3, negative 4, and negative 12. I'm going to try 2 out first, so we drop the 1 down. 1 times 2 is 2. Add these up and we get 5. 5 times 2 is 10. Add these up and we'll get 6. 6 times 2 is 12, so we get our 0 remainder. Continuing off of this one, I'm going to try negative 2, so we drop the 1 down. 1 times negative 2 is negative 2. Add these up, we get 3. 3 times negative 2 is negative 6, so we get our 0 remainder again. And then if we continue off of this one, and let's try negative 3. Drop the 1 down, we get 1. 1 times negative 3 is negative 3, so we get 0. So the list of zeros, we've got x equals 2, negative 2, and negative 3. Now we were also asked to write out the product of linear factors. So we have to think to ourselves, what kind of factor would give us the 0 at 2? Well, that would be x minus 2, because if we were to set that equal to 0, we'd get 2 as the answer. To get negative 2, we'd have x plus 2. And to get negative 3 as a 0, we'd get x plus 3. So there's the list of zeros, and there's the list of linear factors. For 17 and 18, we're looking at finding the domain of the rational function. When we're dealing with a fraction, remember the bottom of a fraction cannot be 0. So for number 17, I would take the denominator of the fraction, the x squared minus x minus 20, and say that cannot equal 0. The left-hand side's a quadratic, so we can factor that out. It'll be x minus 5 and x plus 4. Now normally we would take our factors and set them equal to 0, but we're not using an equal sign this time. We're using a not equal sign. So x minus 5 cannot equal 0, and x plus 4 cannot equal 0. Solving each one, for the first one we'd add the 5 over, so x cannot be 5. And the bottom one we would subtract the 4 over, so x cannot be negative 4. If we look at number 18, again, we're going to take the denominator and say it can't be 0, so x minus 8 is not equal to 0. Add the 8 over, and we get x cannot equal 8 as the domain for that one. In 19 and 20, we're looking at doing a bunch of different things to help us sketch out the picture of this function. We have to find the domain, y-intercepts, x-intercepts, vertical asymptotes, horizontal asymptotes, and then draw out the picture. So for number 19, if we look at part A, finding the domain of the function, remember the bottom cannot be 0, so x minus 1 cannot equal 0, so x cannot be 1. So we've got some sort of domain issue happening there, whether it's a hole in the graph or a vertical asymptote. For part B, in order to find the y-intercepts, we're going to plug in a 0 for our x value. When we do that, on top, 2 times 0 is 0, and 0 minus 1 is negative 1. If we plug in 0 on bottom, we also get negative 1, and negative 1 divided by negative 1 is positive 1. So I'm going to plot that point out, 0, 1. There's our y-intercept right there. For part C, the x-intercepts, we're going to take the top and set it equal to 0. So 2x minus 1 equals 0. I would add the 1 over and divide by the 2, so we get an x-intercept at x equals 1/2. So at x equals 1/2, our graph is crossing the x-axis, so right about there. For part D, looking at the vertical asymptotes, this is where we take the bottom of our fraction and set it equal to 0, so x minus 1 equals 0, and we get a vertical asymptote at x equals 1. So along this x value of 1, we've got a vertical asymptote right there. For part E, in order to find our horizontal asymptotes, this is where we have to look at the powers on top and on bottom. The highest power on top is a 1. The highest power on bottom is also a 1. If the powers are the same, we need to look at making a fraction out of the leading coefficients. So on top, we've got 2. On bottom, we've got 1. So we would say the line y equals 2 is a horizontal asymptote. Now I think on the bottom left-hand side we can get a general idea of what the graph is going to look like. It'll be something like this. But on the right-hand side, we don't really have any idea of what's happening. So maybe what I would do is plug in a couple of values over on the right-hand side to see what our graph is doing. So maybe we decide to plug in 2 for an x value, and also maybe 3. When we plug in 2 for our x value, we should get 3 as our y value. So I'm going to plot that point out. 2, 3 is right there. When we plug in 3, we should get 2.5 as our y value. So that ends up being right about there. And then I think we can get a general idea of what our graph is doing. So it should look something like that when we're all done. Now if we look at number 20, we're going to be doing all of those same things. So for part A, we're looking at finding the domain. So we take the bottom of the fraction and say it cannot equal 0. I would add the 4 over, so we get x squared cannot be 4. Square root each side, and we get x cannot equal plus or minus 2. So we've got domain issues happening at 2 and at negative 2. For part B, in order to find the y-intercepts, we're going to plug in 0 for our x value. On top, we're just going to get 0. On bottom, we'll get negative 4. 0 divided by negative 4 is 0. For part C, in order to find the x-intercepts, we're going to take the top and set it equal to 0. Divide both sides by 3 and then square root it, and we just get x equals 0 as our x-intercept. For part D, in order to find the vertical asymptotes, we're going to take the bottom of the fraction and set it equal to 0. Add the 4 over, and we get x squared equals 4. Square root each side, and we've got a vertical asymptote happening at plus or minus 2. So vertical asymptote at positive 2 and at negative 2. For part E, the horizontal asymptotes, we're going to look at the powers. Again, the powers are the same, so we have to make a fraction out of the leading coefficients. On top we've got 3, on bottom we've got 1. So the line y equals 3 is our horizontal asymptote. Now to get a better idea of what our graph looks like, I'm going to plug in a bunch of values. We don't really know what's happening on the left, so maybe we decide to plug in negative 3 and negative 4. We've got 1 point in the middle, but maybe we decide to plug in a few more values. So maybe we plug in negative 1 and positive 1. And we don't really know what's happening out on the right, so maybe we plug in 3 and 4 to see what's happening out there. When we plug in negative 3, we get 5.4 as our y value, so that's showing up just a little bit off of the graph here. When we plug in negative 4, we should get 4 as our y value, so that's going to be right about here. So the left-hand side of our graph starts up high and then kind of comes in down towards this horizontal asymptote. When we plug in negative 1, we get negative 1. So that's this point right here. When we plug in 1, we also get negative 1. So this bottom piece has kind of a downwards parabola shape to it. And then on the right-hand side, when we plug in 3, we get 5.4. And when we plug in 4, we get 4. So plotting those points out, 5.4 is about right there. And then 4 is right there. So our graph starts out high again and then comes down towards this horizontal asymptote. So we get a picture that looks something like this for the graph. Last two examples, we are solving the inequalities and then graphing out the solutions on a number line. In number 21, since this is a fraction, in order to find the critical numbers, we're going to set the top of the fraction equal to 0. And we're going to set the bottom also equal to 0. So we get 3x plus 3 equals 0 and 2x plus 4 equals 0. The first one we should subtract the 3 over, so 3x equals negative 3. Then if we divide both sides by 3, we get x equals negative 1 as our first critical number. For the second one, I'm going to subtract the 4 over, so 2x equals negative 4, and then divide by 2, we get x equals negative 2. So we've got critical numbers at negative 1 and negative 2. What we need to do now is set up our test intervals. So first interval goes from negative infinity until it hits negative 2. We don't have the equals to line with our inequality, so all of these are going to be parentheses. Our second interval goes from negative 2 to negative 1. Then we go from negative 1 to infinity. Now that we have our intervals set up, we need to plug in a test value. So in this first interval, something between negative infinity and negative 2, maybe we decide to plug in negative 3. When we plug negative 3 back into that fraction, we end up getting 3 as the answer. Since we got a positive number as the answer, that means this is a positive interval. If we look between negative 2 and negative 1, maybe we decide to plug in negative 1.5. When we do that, we get negative 1.5 as our answer. Negative answer means this is a negative interval. Going from negative 1 to infinity, maybe we decide to plug in 0 there. When we do that, we get 0.75 as our answer. Positive answer means positive interval. Taking a look at the inequality, we wanted things that were greater than 0. Well, greater than 0 means positive, so we're looking at this interval from negative infinity to negative 2 and from negative 1 to infinity. So we're going to graph those out on our number line. So let's say negative 2 is maybe right here. This end around the negative 2 is a parenthesis, so we're going to copy that onto our graph, and we're going out towards negative infinity, so we're going to shade this stuff to the left. With our other interval, let's say negative 1 is right here on our number line. Again, we've got a parenthesis around that negative 1, so mirror that on the number line, and then we're shading out towards infinity. So our graph looks something like this for number 21. If we look at number 22, first thing we need to get is a 0 on that right-hand side. So I'm going to subtract the 15 over to the left-hand side. So we get x squared minus 2x minus 15 is less than or equal to 0. If we factor out the left-hand side, we get x minus 5 and x plus 3. Solving each one of these, for x minus 5, we'd get x equals 5, and for x plus 3, we'd get x equals negative 3. So those are our critical numbers, 5 and negative 3. So setting up our intervals, we're going to go from negative infinity to negative 3. Now this inequality does have the equals to line underneath it, so that negative 3 is going to get a square bracket around it, but the infinities on the end will still get parentheses. Then we'll go from negative 3 to 5, again square brackets on those end values, and from 5 out to infinity, square bracket on the 5, parenthesis on the infinity. Now that we have our intervals set up, we need to test them out. So looking between negative infinity and negative 3, maybe we decide to plug in negative 4. We're going to plug this in right here with the x squared minus 2x minus 15 because we have to be looking with the 0 on the right-hand side. When we plug in negative 4, we get 9. Since we got a positive answer, that means this one's a positive interval. If we plug in 0 for that middle inequality, we should get negative 15. Negative answer means this is a negative interval. And then on the end, maybe we decide to plug in 6. When we do that, we get 9 as our answer. Positive answer means positive interval. Now, we were looking at things that were less than or equal to 0, so we want the negative interval that runs from negative 3 to 5. So if we graph this out on our number line, let's say negative 3 is right here, and let's say 5 is right there. These have square brackets around them facing towards each other. So square bracket around the negative 3 and square bracket around the 5. We're looking at the numbers between these values, so we're going to shade between those two square brackets. And that's what our graph would look like for this inequality. That's going to be it for this video. Thanks for watching.